This segment aims to describe the differences between acids and bases, lay out some of the fundamental definitions of the term acid and the term base, particularly as they apply toward the study of organic chemistry. Because what we are going to see is that in the field of organic chemistry, acids and bases play huge roles in a number of different chemical reactions. What we're going to see is that the reaction is absolutely reliant upon the transfer of protons from one molecule to another, or in other words, acid-base reactions. So what we're going to look at to lay the groundwork for understanding those organic reactions that involve one molecule being classified as the acid and the other being classified as the base, we're going to look at the different definitions that we can use to describe acids and bases. So first off, our first definition that we will use to describe acids and bases is the definition laid out by Arrhenius, the Arrhenius acid and Arrhenius base. And this is of the different definitions of acids and bases that we can describe, this is going to be the one that is the most restrictive. So an Arrhenius acid or Arrhenius base is going to be defined, if we're looking at an acid, as a molecule that reacts with water to release a proton, H+, or release H3O+ as a product of the reaction. So acid is defined as a compound that when you place it into water is going to release H+, or in other words, it's going to yield hydronium, H3O+, as a product of its reaction with water. I'm going to go ahead and list an example of this type of illustration of the definition of Arrhenius acid. So we absolutely have to have a reaction with water for something to be classified as an Arrhenius acid. So I'm going to go ahead and plug in water here. I'm drawing out the full Lewis structure of this. And then reacting with that, we can take whatever we want here. I'm going to use HCl just as our simple example to get started, drawing out the full Lewis structure of that. And I'm going to show an equilibrium arrow here. So that's my double-headed equilibrium arrow. Remember, this is not the same as a resonance arrow. This indicates that these two substances are reacting with one another. And in this acid-base reaction, for HCl to be classified as an acid, it is going to have to yield H3O+ as a product of reacting with water or release protons when dissolved in water. So we can show that formation of H3O+ by taking our water, bringing that over, and that's going to grab a proton from the acid. And as a result of that, the bond between H and Cl has to break, and the electrons from that bond go onto the Cl. So what I'm illustrating here, as well as the reaction that's taking place, is I'm showing where the electrons are starting off at and where they're migrating to during the course of this reaction. So we use these electron pushing arrows as a tool, building a map to show what's happening in the reaction. So we're showing that this pair of electrons that I've circled there in red is coming over, and those electrons are what are doing the work of forming a chemical bond to the proton here, the hydrogen from HCl. At the same time that that process is happening, we have to break the bond between H and Cl so that we don't end up going over the allowed valence for that hydrogen. So we'll draw what results from the map arrows that we have just shown here. So our H2O is still fully intact. We still have a lone pair of electrons there on the bottom. And then what I'm going to show here is a bond in red to the new hydrogen, the new proton that was donated from our HCl. So I'm showing that new hydrogen in red. We need to be sure and calculate the formal charge that would result here on the oxygen. If you do the calculation, you're going to come up with +1. And then also as a result of that reaction, we've broken the covalent bond between H and Cl, like we saw here, with that electron pushing arrow. And so we have Cl, and the Cl had 3 sets of lone pair electrons to start with. Those are all still there. And now we will have picked up a 4th set of lone pair electrons because we broke that covalent bond. And during the course of reactions, electrons can't be created or destroyed. They can just move around. So we showed those electrons going on to the chlorine atom. As a result of the pickup of those extra electrons. The chlorine atom, if we calculate the formal charge on it, is going to have a formal charge of -1. So certainly here, our HCl would classify as an Arrhenius acid because of the fact that when we place it with water, we can show that it's reacting with water to give H3O+, which we refer to as our hydronium ion, as a product of this reaction. So this definition of acid is relatively restrictive because it absolutely requires that the molecule be reacting with water. And we're going to see that most of the situations we'll encounter this semester are going to be situations where the organic molecule is not reacting with water, but instead is reacting with some other organic substance. So we will need a broader definition of acids and bases to account for those types of reactions. So the Arrhenius. So now we'll go on and we will give the definition of an Arrhenius base. So Arrhenius bases, much like Arrhenius acids, are going to have a pretty narrow definition, where the definition of an Arrhenius base is a molecule that dissociates in water to yield hydroxide anions. So it's going to be defined as a compound that when you place it into water, it's going to dissociate to release hydroxide anions. Remember that hydroxide anion is OH-. And so an example of this would be if we had something like sodium hydroxide, NaOH. What's going to happen is that when you dissolve that substance in water, it's going to release hydroxide anions. So you'd end up with Na plus and OH- because that is an ionic bond between those two substances. So, like we said, these definitions are relatively restrictive. And so we need something broader to encompass the wide breadth of different types of organic molecules that engage in what we could call acid-base reactions to help us classify what's going on in different types of reactions that we'll get into later on. So another definition that we can add to our mix of definitions of acids and bases, rather than referring to a substance as an Arrhenius acid or Arrhenius base, we can broaden out the definition a bit more by going into what we refer to as Bronsted-Lowry acids and Bronsted-Lowry bases. So that's what we're going to talk about now, is what we would define as a Bronsted-Lowry acid and a Bronsted-Lowry base. So this is our second way of defining what is an acid, what is a base. And this definition is going to be a bit more broadly encompassing. So we define an acid, based on the Bronsted-Lowry definition, as being a proton donor. So H plus is our proton, so we define it as a proton donor. In other words, during the course of the reaction and going from reactant to product, the acid is going to lose a proton. So when we look at the relationship between the starting material and the product, we will see that something that's defined as an acid during the reaction is going to lose a proton during the course of that. So you'll see that a proton is missing from the substance once we go from reactant to product. So an example that we could look at for something that would fit this Bronsted-Lowry definition of acid and base is if we take a look at sodium methoxide, NaOCH3, and we react that with HCl. We're going to draw an equilibrium arrow here, as is custom for acid-base reactions, even though many of these reactions, such as this one, are going to have an equilibrium that's so far toward the side of the products that we would essentially consider the reaction going to completion. So as we look at this and start to try to sort out what's happening here, we need to keep in mind what is actually the molecular structure of sodium methoxide. So in sodium methoxide, there is a large electronegativity difference between sodium and oxygen. Sodium's at the far left side of the periodic table, oxygen at the far, much further to the right. So sodium and oxygen are going to engage in an ionic bond. So the electrons are going to be fully transferred to the oxygen. So therefore, the sodium will take on a plus charge. Oxygen will have 3 sets of lone pair electrons and a negative formal charge. It'll be covalently bonded to that CH3. And we will also have HCl available there. So when we mix these two substances together, what's going to happen is that if we write out our Lewis structure here for HCl, the electrons from the oxygen atom are going to enable it to act as a base to come over and grab a proton from the HCl. That's going to force the bond between H and Cl to break. And as a result of that reaction, based on the electron pushing arrows that we're showing, our oxygen is going to form a new bond to our proton that was donated by HCl. So we have a H, and then our covalent bond, which I'm showing in red, that is just formed, bonded to our OCH3. Our oxygen atom is going to still have two sets of lone pair electrons, because we had two sets here and here circled in yellow that aren't participating in the reaction. That third set that I've circled in red was the only set participating in the reaction. That's what became the covalent bond that we show in red over here. So we've got our newly transferred proton, and then our other product of this reaction is that we broke that bond between H and Cl, sending the electrons from that covalent bond onto the Cl. So our Cl is going to have two electrons there, or a lone pair in other words, and we need to calculate our formal charge there, which would be -1 on that chlorine atom. Additionally, that sodium has carried through as just a spectator ion. A spectator ion is not participating in the reaction in any way, shape, or form. You could think of it as being just along for the ride. But certainly here in this case, our HCl is going to fit the definition of a Bronsted-Lowry acid because of the fact that in going from the reactant to product, the HCl is losing that proton. So it went from being HCl to just being Cl-. Therefore, HCl is of course defined as our acid here. Our base would be defined as our OCH3-. That's what's accepting the proton. So we can go ahead and write in that definition here for a Bronsted-Lowry base. A Bronsted-Lowry base is defined as a proton acceptor. So you're going to see that acids and bases are going to react with one another here, where the base is what's obtaining the proton during the course of the reaction. The base is going to be gaining a proton during the reaction as the acid loses a proton. So base is going to gain the proton in going from reactant to product. When we think about what is possible in terms of what can act as a base, in order for a molecule to act as a base, typically what's required is that the molecule generally must have a lone pair of electrons or pi bonds. And it's going to be this lone pair of electrons or the pi bonds that enable that base to accept the proton. So what we saw up top here with our sodium methoxide reacting with HCl was that the lone pair of electrons were enabling the OCH3 to act as the base to grab the proton. So a base, what to look for when you're thinking about what could possibly act as a base in a reaction, is that we're going to see that bases are generally going to have lone pair electrons, and I'm abbreviating lone pair there as LP, or pi bonds. So remember that pi bonds are double bonds or triple bonds. And so that's what you need to be on the lookout for when you're thinking about what's going to be able to act as an acid or base. So we'll go back and go ahead and characterize our NaOCH3 as our base here, based on the Bronsted-Lowry definition, because certainly it's picking up a proton as we go from the starting material to the product there. Because we look at the relationship between the OCH3- starting material and our final product that we end up with, we see that this OCH3 is gaining a proton during the course of that reaction. So therefore, it is qualified as a base. So let's take a look at another example of compounds that fit this definition of Bronsted-Lowry acids and bases. And let's this time go with, we'll start with an alkene, a molecule with a carbon-carbon double bond. I'm just going to fill in some groups here, some CH3 methyl groups into this condensed structural formula. And we're going to react with HCl again. And we're going to try to use electron pushing arrows to show what's happening in the course of this reaction and to predict what the product would be of this acid-base reaction. So first off, we need to predict what's going to be the acid, what's going to be the base. Well, HCl we're going to predict as our acid. Our alkene we're going to predict as our base. And going back to this Bronsted-Lowry definition, a base being a proton acceptor, and in order to accept a proton, what we use to accept those protons is we use lone pair electrons or pi bonds. So as we look at a molecule, we try to analyze what part of that molecule is able to act as a proton acceptor, what's able to pick up a proton from the acid. We need to look for lone pair electrons or pi bonds. And so as we look for lone pair electrons or pi bonds in our alkene, we really only see one possibility, and that's the pi bond there that I've highlighted in green. So what we're going to do is we're going to take that pi bond, and we're going to bring that over. So our arrow starts at the electrons of the pi bond. It's going to come over and journey over here to form a bond to the acid, to form a bond to the proton, hence allowing our base to fit that definition of being a proton acceptor. It's going to be gaining a proton during the course of the reaction. HCl, the bond between H and Cl breaks, going on to the chlorine, and we'll go ahead and write out what would result from this set of electron pushing arrows. So let's take care of hopefully the easy part of this first, and that is the chlorine. So our chlorine started off with 3 sets of lone pair electrons. Those 3 sets of lone pair electrons are still there, and in fact, due to that electron pushing arrow that's moving the electrons from the HCl covalent bond onto chlorine, we need to put another set of lone pair electrons in there. If you calculate the formal charge on that, it's going to come up to -1. Then, with our alkene, our connection between atoms is still the same as it was to start with, so I'm going to redraw the skeleton exactly like it was, except that the pi bond is no longer going to be there, and it will have been used to form a covalent bond to the hydrogen, to the proton. So we're going to go ahead and plug that proton in there. So what we're showing here is that this pi bond, those 2 electrons from that, remain tethered to one of the 2 carbon atoms of the double bond. It doesn't matter which one at this point because the molecule is symmetrical. The alkene is symmetrical. So it comes over and it forms a bond to that proton. So the carbon-carbon double bond electrons, those pi bond electrons, are going to go over and grab that proton, allowing that proton to be bonded to one of the 2 carbons that was originally part of the alkene. So we've done that. And then those 2 CH3 groups are still right where they always were. So we'll go ahead and plug that in. And then we do need to keep in mind the question of where's the formal charge going to be. We can predict there should be a positive formal charge somewhere in this molecule because of the fact that if we look at the reactant side of the equation, we see that the net charge on the reactant side is 0. And so therefore, the product side also has to be 0. So that's one way to kind of keep yourself on track about whether you have found all of the formal charges or not, is it should have a charge balance between reactant and product. So if we look at our carbon atom there on the left that I've put the plus sign on, that carbon as a result of the reaction only has 3 bonds to it. So that's going to be a positively charged carbon, or a so-called carbocation. Carbo for carbon, cation because it's positively charged. This is a relatively unstable intermediate, so what would happen here are some additional reaction steps on later down the road to yield a stable final product. This is what's going to result from the acid-base stage of the chemical reaction that's going to go on between an alkene and HCl. And we're trying to just classify things here as acid and base at this point. So we're classifying our reactants as acid and base. The other thing that we can do is we can classify our products as the conjugate acid and conjugate base. So the base, once it picks up a proton, is always going to become classified as the conjugate acid. So we're going to classify our product here that has picked up that extra proton in green as our conjugate acid. On the other hand, our acid, which has lost a proton during the course of the reaction, is going to become classified as our conjugate base. So our conjugate base would be that Cl minus. So it's always going to be the case that once the acid loses a proton, it becomes the conjugate base. Once the base gains a proton, it becomes the conjugate acid. And the reason that we refer using this terminology is because of the fact that we consider acid-base reactions to generally be equilibrium reactions, reversible reactions. And as a result, if we're looking in the direction of going from right to left, if we started the conjugate acid and conjugate base, the thing that's defined as the conjugate acid, if we're going in the left-hand direction, is going to be what's losing a proton and going from conjugate acid back to the left. On the other hand, the conjugate base, as we go back to the left, is going to gain a proton. So that's how we come up with these definitions of acid base, conjugate base, and it's good to be able to classify things as such so that we can describe what's going on in different chemical reactions. So even with the Bronsted-Lowry definition of acids and bases, we still haven't encompassed all of the different types of situations where we would describe a reaction as being an acid-base reaction in the field of organic chemistry. So that brings us to our third definition. So we had the Arrhenius definition, Bronsted-Lowry, and now we have what we refer to as the Lewis acid and Lewis base. This is going to be the broadest definition of acids and bases, the most widely encompassing definition that we can use to describe what is an acid and what is a base. So we're going to look at our Lewis acids and Lewis bases, or a Lewis definition of acids and bases. So when we're talking about a Lewis acid, the Lewis definition of acid refers to a molecule that accepts a pair of electrons to yield a new covalent bond. So during the course of a reaction, we're going to see that the acid is defined as the molecule that's going to receive or accept. I'm using receive and accept as synonyms here. So it's going to receive a pair of electrons to yield a new covalent bond in going from reactant to product. So what we're going to see is that an atom and the electrons that are associated with it are going to become newly bonded to our acid as we go from reactant to product. And that's a very broad definition of acid because you'll notice that the term proton doesn't even come into play here. So a Lewis acid doesn't even necessarily have to involve transfers of protons around. It involves just that the acid is defined as receiving a pair of electrons from a donor to end up with a new covalent bond in the product. We'll do an example of that in a moment. And what goes along with the Lewis acid, of course, its buddy is the Lewis base. And the Lewis base, rather than accepting or receiving a pair of electrons, what the Lewis base is going to be doing is it's going to be donating that pair of electrons. So a Lewis base is going to be the source of the electron, so it donates an electron pair to yield a new covalent bond. So we're looking at really acids and bases as the difference being whether they are donating a pair of electrons, which would make the molecule qualified as a base, or receiving a pair of electrons. And if we go back to our example above, so we just go back up here to our Bronsted-Lowry definition of acid and base. We described our base here on the left as being our alkene, the acid as being the HCl, and these molecules would also fit the Lewis acid, Lewis base definition as well, because certainly our acid, HCl, that proton is receiving an electron pair. You can see that arrowhead from the alkene coming over and attacking that proton, meaning that that proton is receiving a pair of electrons from the alkene. On the other hand, the base, the alkene, is donating that pair of electrons, and that base is going to obtain a new covalent bond as a result of that. The covalent bond is going to go to the proton in that case. So let's take a look at something that would meet these criteria of being a Lewis acid and Lewis base pair. And what we're going to look at is an example of a carbocation, such as the carbocation that we yielded in the reaction above, where we were doing the Bronsted-Lowry acid and base definition. And one of the things we created was this carbocation. And we mentioned that this carbocation is relatively unstable. It's typically a reaction intermediate rather than something that would persist long term. We also had in that same mixture a chloride anion, Cl-. And what we're going to show here is that what happens is that the chloride anion, being negatively charged and having an excess of electrons, is very, very attracted to that positively charged carbon. Opposites attract after all. And so it's going to come over and form a covalent bond to that carbon of the carbocation. So we can go ahead and draw the product that would result from what we've just shown here. So I'm going to show in red the new bond to the chlorine atom. The chlorine's still going to have 3 sets of lone pair electrons. The 4th set of lone pair electrons became that red covalent bond. The carbon that we bonded to still has 2 bonds in blue to CH3 groups. And it doesn't matter, by the way, that we put the chlorine aim downward or upward here. What I'm trying to do is just spread the bonds out as far as possible. Since we have 4 bonds to carbon, we want those separated by as much distance as possible. So I've spread those out. And then the rest of the molecule remains unchanged. So I'm just going to fill in the other carbon with the 2 CH3 groups bonded to it and the hydrogen bonded there. So if we take a look at the reaction that I have just shown here and try to classify our reactants as acids and bases based on the Lewis acid and Lewis base definition, what we would see is that since our acid is defined as what's receiving an electron pair, so the recipient of the electron pair here is where the arrowhead is ending up at, because that's indicating where the electrons are going to. That's indicating what's obtaining the electron pair during the course of the reaction. So we would define our structure on the left here, our carbocation, as being our Lewis acid, and our chloride anion as being our Lewis base. Because our Lewis base, by definition, is what is going to be donating the electron pair, and the donor is where the electron start at. So we see the start point of the arrow, and that indicates where the electrons are being donated from, or who is the electron donor. So our electron donor there is certainly our Lewis base coming over, donating a pair of electrons to our so-called Lewis acid, which is accepting those from that. And you'll notice that certainly a new covalent bond is formed here. That's what I'm circling in yellow here in our final product. So this definitely meets that definition of Lewis acid and Lewis base. A term that you should be familiar with that goes along synonymously with Lewis acid and Lewis base is the term nucleophile and electrophile. So the term Lewis acid, that is our recipient of a pair of electrons during the course of the reaction, is defined as an electrophile, or could also be described as an electrophile. So an electrophile, if we tear apart that word, the term phile means love. Electro is referring to electrons. So a Lewis acid is an electron lover. In other words, it really wants the electrons from the Lewis base. So we define the Lewis acid as an electrophile. And on the flip side, we define our Lewis base as a so-called nucleophile. So our Lewis base is defined as our nucleophile. So just as in the term electrophile, where phile meant love, here phile again means love, nucleo means that the Lewis base loves the nucleus. It wants access to a nucleus. That is why it is donating an electron pair up here to come over and mate with the electrophile. So nucleophiles and electrophiles are the match made in heaven here. The nucleophile really wants access to a nucleus. The electrophile really wants access to electrons, and the nucleophile has that excess of electrons to provide to it. So our Lewis base, in order to donate that electron pair, is going to have an excess of electrons, and it gets that excess of electrons much like looking at the definition of a Bronsted-Lowry acid or base. The excess of electrons comes from having a lone pair or a pi bond. So for Lewis acids and Lewis bases, for Lewis base in particular, we have to have a lone pair or a pi bond to act as that donor of electrons, because Lewis bases, or synonymously nucleophiles, are going to be able to donate electrons. So that's our three definitions of acids and bases: Arrhenius, Bronsted-Lowry, and Lewis, going from the most restrictive definition, Arrhenius, to the broadest definition, Lewis acid and Lewis base. And we're going to be seeing these terms nucleophile, electrophile throughout this term. So it's really one of the solid core concepts of organic chemistry to get down is what is a nucleophile, what is an electrophile. Definitely know those definitions.